speaker is Biehl from Cross Labs, and his presentation title is Designer Uncertainty and Agent Uncertainty. Please.
Okay, can you hear me?
Yes.
No?
Yes, yes.
Yes, okay. Okay, so this is work with Nathaniel Virgo also, who you saw before. And yeah, it's also funded by the same agencies. So I guess in this work, one way to kind of see this work or put it into some kind of scope is to try to formalize the process of designing artificial agents. Why should we do this? Maybe it will help us to think a bit more precisely about these design choices, and then also maybe if you read machine learning papers, they always have things like tons of different things, and it takes a while to always figure out which problem they're actually solving or how they're setting it up. So maybe we could kind of classify this. And then another thing that we could use this for is maybe we could find out why we have such trouble designing autonomous agents or open-ended agents or things like this. Okay, but that's just as a kind of background idea. So I'm going to be talking about something a bit more specific, and that is designing artificial agents using probabilistic inference. And then I'll give kind of two maybe applications of this approach. So one is how to model some kind of designer uncertainty or problem uncertainty, and the other is how we can express the agent's uncertainty in this framework. And then recap and maybe mention some issues. Okay, so if we design an artificial agent, then usually what we know is we usually know at least something about the dynamics of the environment. And then we know what kind of sensor values the agent will have available, and then what kind of actions it can take, and also what goal it is trying to achieve or it should achieve. And then what we want to find is maybe the dynamics of the memory of the agent, and also how it should select, which actions it should select, depending on the memory, such that it achieves actually its goal. So I'm going to call the environment. So here on the right, you see some kind of representation of this, and this is a Bayesian network, and the environment are those E nodes, and these are like in the end 3 time steps, or with a 4th environment state. And there's a goal state which only depends on the on E3, so the 3rd environment state here, but it could depend on more variables. And then you see that at each time step, the environment produces a sensor value S, and then this sensor value gets so that then the agent's memory can use this sensor value and then produce an action. And then this action influences the next environment state again. And then this is kind of how this works. And this is this framework is like to set this setting up this problem like this is kind of very general. Like you can represent many machine learning problems like this. But you sometimes have to change this graph a little bit, of course. And so you see here the nodes, 2 nodes are gray, and those are the ones that you want to find, kind of. You want to find the actions and how the memory updates, because that's what you do when you design an agent, I guess. You don't always, you not only, like in general, you not only do you have to figure out what actions the agent should take, but also what it should remember. And that's why you also don't know the memory update, or why you need sometimes the memory update. Okay, and so yeah, we're gonna use, so the way we're gonna represent this kind of design process of an agent is as these kind of Bayesian networks, where we put gray nodes where for variables that we don't know the dynamics of, and white nodes for those where we do know them. And then we have this goal variable. Okay. So maybe the quite powerful thing you get if you actually write down this whole Bayesian network for the agent you want to design is that in principle, all you can kind of use an algorithm to find those unknown kernels, or at least, I mean, first you can write down the problem that these these unknown kernels should solve. And that's so all you have to do is basically maximize the probability of achieving the goal. So you look for those gray nodes that maximize the probability that your goal node is equal to 1, which is in our case, which is how we represent that the goal is achieved. Maybe I should mention, if you have some reward function, you can kind of use the same approach. You just have to make sure that the goal node, the probability of achieving the goal depends on this reward function in some way. Okay, but the thing is that you can kind of derive your agent in this way. So its actions and its memory dynamics by maximizing this probability. And maximizing this probability is actually a well-known problem. It's a maximum likelihood inference problem, and there are some algorithms that can solve this problem. In some cases, I say here just maximize this probability. It's actually quite a tough problem. So we can't easily solve this, but it's a well-defined problem. Let's put it this way. Okay, and in this way we could, like, in principle, this automates the design of an agent. Okay, so that's kind of the first part of the talk. Now, what can we? Now I'm going to give 2 examples of what you can do if you do this. So one thing is, let's say there's there are like 2 different situations where you can use this designer uncertainty. The first is if you as the designer are basically uncertain about the environment dynamics. So you don't know, you want to make an agent, but you don't know actually which one of a few different possible environments this agent is going to be faced with. That's one situation. And then another situation, which is kind of is in the end kind of the same situation, is when you actually want to make your agent capable of dealing with different environments. So maybe you know that there are different environments and you want to make sure that your agent can deal with all of them. So to do this in this kind of framework, what you have to do is you introduce a new variable, I call it phi, and which selects basically which environment your agent is going to be faced with, and you put some prior distribution over phi. So that reflects your uncertainty about which environment it's going to be faced with. And then, this other setup we had before turns into this setup where you have this additional variable phi. And the nice thing is that if you then run this, solve this problem here, it's called also planning as inference. So you maximize this goal probability in this setting, then actually what the resulting agent will actually, if it's necessary to solve the problem, it will actually explore which environment it's faced with. And yeah, if it can, it will find out which environment it's faced with and solve the problem. So this is also kind of like meta learning. So we can nicely represent this in this framework. Then maybe what we would also want to know sometimes is, if we create such an agent, what does this agent actually subjectively think? Maybe we would want to know, or what does it believe, maybe. And if you remember Nathaniel's talk, that's kind of something we are also investigating. So you could try to interpret this agent's memory here as a Bayesian, in terms of Bayesian inference, and then in this way try to figure out what this agent is thinking about. But this, of course, might be very difficult because then you don't know you don't know from the beginning what's the possible interpretation. But what we can do instead to make sure that we have an interpretation is we can actually fix the memory dynamics of the agent. So instead of, like before, we said, okay, we don't know the memory dynamics and we want to infer them. But now, if we want to make sure that we can interpret the agent in terms of Bayesian inference, then we can actually design the memory dynamics ourselves and only find out and only infer the action policy. So what we have to do then, of course, is to make sure that the memory dynamics we design have a Bayesian, consistent Bayesian interpretation. Yeah, you can do that. You use the conjugate prior construction that Nathaniel mentioned. And then this means basically that you get, so what this then means is that you can actually, you have these interpretation functions, interpretation maps. I think Nathaniel also called them psi. And okay, like these nodes are they are grayed out because those are deterministic functions. They're not stochastic. They cannot be stochastic. They must be deterministic. And so if you have this psi, that means that you have basically this function that maps each state of the agent to some belief state. And then if you want to know what the uncertainty of this agent is, then you can just use the Shannon entropy of this belief distribution. And maybe one other thing you can do is to make your agent basically maybe something like curious. You can measure the information gain from the first state to the last state, and then which is the KL divergence between the last belief and the first belief. And this gives you a measure of how much the agent changed its belief over time and became more certain. Okay. Yeah, and then, so if you want, you could then also use this as a kind of goal. So you can kind of, instead of having some other goal of that you want to achieve in the environment, you could turn this kind of information gain into the goal of this agent and have some kind of intrinsically motivated agent. Okay, that's basically it. I'm going to skip the recap because I'm way over time. But what I want to say is maybe that maybe you ask yourself why doesn't everybody draw a Bayesian network in the beginning of their paper so that we know which problem they're solving. There are some good reasons for this. For example, you can't always use a Bayesian network. So a simple problem is that if you don't know how many time steps your agent will take to solve it, then you can already not draw this Bayesian network. And also actually finding the correct Bayesian network representation of what you know about the problem is also, it can be kind of subtle. So we hope that in the future we'll find a more generally applicable representation that's hopefully also easier to represent the design of artificial agents. Okay, that's it. Thank you.
Thank you. And any questions or comments? Takashi, please.
Hi, Martin was very interesting as usual. I have one question. When we say agents or agency, I think we expect some sort of autonomy, right? Once there is no autonomy, you can call it free will. I don't think we can call it, agency. Well, just achieving goal, and then maybe you can call it, like a belief network. But still, if we want to say agency or there's an agent, then I think we need to have something that is autonomous inside. I don't know if you have any comments on this.
Yeah, so I guess that's one reason why I said I mentioned autonomy in the beginning. So I think autonomous agents are special, and actually I agree. So these agents that we treat here, we assume kind of that we have this goal. Like I always mentioned that there is this goal, and it's a kind of, maybe it's a limited definition of agents. Because like, yeah, I think autonomy is a kind of, I think autonomous agents are something that maybe doesn't really fit in this framework at the moment. Because, for example, like the autonomous agent, especially if you think that the autonomous agent, or if your definition of autonomy involves that the agent kind of ensures its own survival, then I don't think this framework can deal with this at the moment. I think,
yeah. Well, if you say so, then my question is going to be like, so what this model is for? I mean, well, you can make a model that achieves this kind of thing, right? I mean, what sort of formalism that you are achieving now?
Yeah, I guess so. I think our hope, and it's only a hope, is that if we try to push this the boundaries of this formalism further. So, like I said, the Bayesian networks is not going to be enough. We already kind of know that we will have to stop using Bayesian networks, but there are some theories. So in general, with Bayesian networks, you cannot represent all probability distributions. but the planning as inference framework, for example, at least it can in theory deal with all probability distributions. So probability might still work, but we have to drop the Bayesian networks. And we hope that we can, for example, right, let me see. We hope that what we can maybe use one day is some theory where the value of the variables, where basically the network itself could change its structure depending on the value of some variable in the network. So this is impossible for Bayesian networks. But if we can extend this framework to such things, then maybe, and it's just a hope. It's just a hope. Maybe we can also start talking about more interesting agents that ensure their own survival. But yeah, I think it's a very good point, and we are not really sure yet how to solve it. I think for us this is already kind of nice because we have this kind of two versions of uncertainty, but it's much more. At the moment, it's much more about AI than about A-Life, I would say.
I agree. Yeah.
This was a long answer. I'm sorry.
Any other questions? Just a short one from me. I can't believe that you are interested in designing the artificial agent. So I thought it's like usually when we apply the Bayesian inference, it's a kind of we stand on the agent point of view, and then environment can be uncertain, have an uncertainty, right? And then, oh, sorry. And but in this model, in this model, I thought you tried to make a model of the observer. So from the observer, the internal state of the agent is they have an uncertainty.
It's also
yeah.
Yeah.
It's like Nathaniel's talk. He tried to create the interpretation, inference world. And then from the designer's point of view, the inference world of the agent is a kind of observer. No, I can't explain, but you try to create please.
Yeah, I think it's I'm not 100% sure, but
that sounded exactly right to me.
Yeah. So yeah, the perspective here is kind of very, so I mean, this is kind of tough. We draw this Bayesian network and it kind of contains an agent. And actually, we also put in our uncertainty with this node up here about what the environment is that this agent will be faced. And then since the agent is inside this system, we can also ask, but what does the agent know at different time steps? Because we might, like if we don't design the agent's memory ourselves, then we actually will not know what the agent knows. So yeah, that's kind of, it's a little bit also the power, I mean, it shows a little bit the generality of setting this up like this, with this, where the agent is inside the Bayesian network. And you can model your own uncertainty about what environment there will be. It's, yeah, I'm not sure if that clarified your question.
Thanks so much.